Okay, this video is in response to a question a friend of mine asked me. So I have the question here in front of me. So she says, take 13 tiles and gives particular ones and choose a particular string of the characters, which she chose Rotor, which is an excellent choice. Good movie. And then says, okay, you're going to make a string of these characters. So presumably you're drawing these characters out of a bag, writing it down, putting the character back in the bag. So you've got a indefinitely long string of characters developing, and you're going to stop once you've just obtained the desired substring. So basically she's going to pull out tiles at random until she pulls out in order, R-O-T-O-R. And the question is, what's the expected value for the length of the string? And she said when she tried to do this herself, like computer simulation, got somewhere between 9,000 and 11,000 usually. So she was wondering, how do you go about solving a problem like this? In this video, I'm going to talk about, so motivated by this, I'm going to talk about some of the basics of Markov chains, which in principle, I'm going to tell you how to solve this problem. Computationally, though, it's quite difficult, and I'm not really a computational guy. I mean, basically, what we're going to have to do is find either large powers or an eigenspace of a very large sparse matrix. But I don't actually know those sorts of things. But anyway, in this video, I'm going to tell you how you set this up as a Markov chain problem and turn it into a matrix problem. And then, in principle, that tells you how to solve a question like this. All right. Well, let's get started. Let me actually take this particular problem just kind of as an example. So 4, 3, 2, 2. Okay, I don't know if I'll remember those numbers. Let me set it off to the side. So I've got 4 O's. These numbers don't really matter, but I'm just kind of, just for the sake of definiteness, 2 B's, 2 E's, 1 R, and 1, I don't know what the last number is. Okay, I've already got everything for Rotor, so I'll make it a Z. All right, and that is 13 of them, so I got them all. And presumably we're just going to start writing down our answers. You also have to forgive me because my stylus is broken, so I'm having to write with my finger, and sometimes my tablet thinks I'm wanting to move the screen when I'm really wanting to so on and so forth. We keep generating these random guys until we get what we want. Well, we don't care about the whole string. All we care about is blocks of 5. So we can think about, here we have our initial block of 5, and then our next one. So let's write them down in sequence. So I start out R-O-T-O-R-Z, T-O-R-Z-B, and then what's next? Next is O-R-Z-B-E, and so on and so forth. So I'm taking these blocks, I'm taking 5 letters at a time, moving down until I see the word Rotor. I can think about these as states of a stochastic system. So, and we'll notice something very simple, which is the thing that kind of distinguishes this problem is that, well, these states are 5 letters long, and the last 4 letters of one state correspond to the next 4 letters of the next state. So, if we think about this in terms of what we're going to call a Markov chain here in just a second. If we say, okay, phi and psi are two states, well, first of all, we see that the probability of getting from psi to phi next is 0 if the last 4 of psi are not the same as the first 4 in phi. And then if they are the same, well, it's, say, p of x. If they are the same and phi ends in an x. So where these probabilities here are kind of what we started with. So if the new one starts with an O, the probability of hitting the new one, if those first 4 line up right, would be 4 out of 13. If the new one ends in an E, then the probability of hitting the new one, given that those first 4 line up right, would be 2 out of 13, and so forth. So that's kind of the scenario. We know if we know which state we're on now, that's all the information we need to compute the probability of the next state. It's going to be 0 if the new state doesn't start with what our current state ends with, and it will be a probability that we're given in the setup if it does. So this is exactly the sort of thing that's called a homogeneous Markov chain. So homogeneous Markov chain is you've got some sequence of states, so phi1, phi2, phi3, going on forever. And the important point is that the probability of phi n plus 1 given phi n is, well, the homogeneous part says it's independent of n, and the Markov part says that this is equal to, well, actually, let's not say it that way. Basically, this is going to be the probability of any particular state given a predecessor. So, all right. Okay, I feel like I'm saying something confusing, but all it really says is what we had before. It's if you know where you are, that's all the information you need to compute where you're going to go next. You don't need to know how you got to where you are. You just need to know where you are. You don't need to know how far down you are in the sequence. All you need to know is if you know where you are, you can find the probability of where you'll go next. That's a homogeneous Markov chain. Okay. So there's a couple of words that go along in Markov chains. It should be leads instead of leads to psi. All this means is if you're at phi, there is a chance somehow you will wind up at psi if you keep on going forever and ever. Maybe not in one step, but if you're currently at one state and you do this several times, you could eventually wind up at psi. So this is called phi leads to psi, and if they lead to each other, this is actually equivalence relation. So if phi leads to psi and psi leads to, I don't know, pi, then, well, there's a way to get from phi to psi after enough choices. There's a way to get from phi to pi after enough choices. Then you can definitely get from phi to pi. So it's transitive no matter what. And if it happens that they both lead to each other, then that makes an equivalence relation. So excuse me a second. So in our problem, well, it really doesn't matter what string I'm at. Like if I go, I don't know, B-E-T-Z-O, if I want to know, can I wind up at rotor? Well, I just write rotor as my next 5. So definitely any state will lead to rotor, possibly. And vice versa. If I'm at rotor and I wanted B-E-T-Z-O, well, I just write B-E-T-Z-O at the end of it. So rotor leads to any state. So this is a very, very special circumstance where actually every state leads to every other state. And this is a scenario called irreducible. So like in most branches of math, one of the things you do in Markov chains is you attempt to break down this entire process into the simplest pieces. This piece is as simple as it can get because it doesn't matter how long you go, there aren't any states that are really going to drop out. You're going to need all the states, all forever. Okay, so that's nice. There's some words that go along with this, which we really don't need to worry about, but there's recurrent and transient. So those words mean exactly what I was saying. A transient state is a state that could, under certain circumstances, eventually disappear. I mean, you go there, once you leave, you possibly never come back. A recurrent state is a state that with probability 1, you will always return to. And it's not very hard to prove, but I don't think I'm going to do it right now. If you have finitely many states, well, you would probably guess at least one of them has to be recurrent. I mean, it's kind of a no-brainer. I mean, if you have infinitely many states, you can just keep moving down the line. But if you've only got finitely many states, there's got to be some state you keep coming back to. No, so that's kind of intuitively obvious. It's not that hard to prove, but I don't really feel like it. Other thing that's pretty clear is if you have two states that communicate or that lead to each other, then they're either both transient or they're both recurrent. So again, that's not very hard to prove either, but I mean, it's intuitively obvious. If you keep coming back to phi and phi leads to psi, well, you're going to keep on hitting psi after you hit phi. And same thing, if you keep on coming back to psi, then, well, you're going to keep on coming back to psi too. So going back to our original problem, because it was irreducible, and finitely many states, the first thing we see is that all states are recurrent. Which answers kind of a sub-problem of the problem that my friend gave me. I mean, before you ask what's the expected number of times you have to go before you get to this state, the first thing you really should ask is, are you going to get to this state with probability 1? And the answer is yes, you will get to this state eventually with probability 1. So, all right. Something else that can happen in general that isn't going to happen in our problem, but just so you've seen these words, there is something called positive recurrent versus null recurrent. Just because you get to the state with probability 1, the expected value for how long it takes you to get to the state could be infinite. And when that happens, it's called null recurrent. Since we only have finitely many states, there's no way. So just like two things are, if one's recurrent, the other one's recurrent. If you have two states that lead to each other, if one of them's positive recurrent, the other one has to be positive recurrent. And because there's only finitely many states, there's got to be at least one positive recurrent. So this answers another question. So is the probability we get to the state we want eventually equal to 1? That was yes. Is the expected value of the time finite? This is also yes. So since we have this irreducible Markov chain with only finitely many states, we should get to every one of them in a finite amount of time. Okay. So that brings us to the big question, how do we compute this expected value for the amount of time it takes anyway, yeah, I don't want to be terribly formal, so let me not write that down. But how do you compute the expected value for the time it takes to get to a state? Well, that's kind of not quite well defined because you can't really start in a random place. But what people tend to look at is, let me change back to phi because that's what I've been using in this one. They look at the expected value of the time it takes to get, if you start at a state, to get back to that same state. And they call this the mean recurrence time. So that's what I'm going to tell you how to compute. As far as the problem we actually started with, I mean, once you go 5 steps out, no information has any relevance, right? I mean, once I've added 5 more letters, who cares what 5 letters I started with? So you could replace this by anything else. It's not going to change the time to get to that state by more than 5. I mean, so it's, and this problem is kind of silly to make that distinction between starting at the word rotor and ending at rotor versus starting anywhere and ending at rotor. Is the expected values, I mean, in general, they're basically the same, but especially in this situation, just the way it's set up, they're obviously basically the same. Okay. So how do you go about computing this? Well, there's a big, let me give you one more concept first, which is a steady state distribution. Which, if you've seen physics, this will make a lot of sense. And basically, you've got all your states that you could possibly be in. But in physics, they let you do mixed states. So C1 phi1 plus C2 phi2 plus Cn phi(n), where these are numbers that add up to 1. So, I mean, in physics language, the states that we expect the system to be in would be like pure states, but it could actually be in a mixed state. It's some superposition of those pure states. Why is this an interesting thing to do? Well, I mean, you can, well, the reason is because there is a steady state. That's the main reason you want to do this. But just kind of by extending linearly, or I guess affinely, you can find the probability also for mixed states. So that you wind up in some mixed phi given some other mixed state psi. And the thing about this is there's always a steady state, which is defined by the probability that you wind up at pi given you started at pi is 1. And this happens anytime you've got an irreducible Markov chain with finitely many states. You have this guy. Actually happens for infinitely many states too, but the proof is quite a bit more difficult. So anyway, and basically what's going to happen is if I start in any state, pure or mixed or whatever, so phi1, and I just kind of go down the progression, it's going to converge to the steady state. Okay, I'm trying to talk around something without talking around it. But the point is, eventually that's what happens. So you'll have some distribution of your actual probability states. So your states you started with, if you hit it with this Markov chain transition matrix enough times, it will converge to this steady state distribution. So let me not worry about that. The point of this steady state distribution is that it's given very explicitly. The phi component of it is 1 over the expected time to get to phi, which is sort of makes sense if you think about it. It's like if you think about the long-term behavior, well, however long it takes you to get from phi back to itself on average should be about the amount of time you spend in state phi. So my claim is that you can actually compute this steady state vector using linear algebra. And it's really easy because, well, if you look at this equation, well, P, I actually said transition matrix and didn't do it, but I can make a matrix by going, I'm using as and j's again because that's what everybody uses in Markov chains. I don't know why I started out with phi and psi. I guess I was being silly. But I can make a matrix by saying, okay, well, the probability of phi given, or the phi psi spied is the probability of phi given psi. Well, you can kind of do a little simple calculation. So as if you look at the square of the matrix, well, that is the probability that you get from psi to phi in 2 steps. And same thing, if you cube the matrix, that's the probability you get from psi to phi in 3 steps, and so on and so forth. So in some sense, these probabilities are just being imparted by multiplying by this matrix. So if you want to compute this steady state distribution, well, all being the steady state vector would say is, well, if I take this matrix and multiply it by, actually that's backwards, it turns out that these are all right multiplications. If I multiply this this distribution by p from the right, it should be invariant. So basically this is a row eigenvector with lambda equals 1. And there's some general theory, basically the Perrin-Frobenius theorem, that says, for one thing, there's only one eigenvector with eigenvalue 1, so you don't have to worry about finding the wrong one. You'll also, another thing that goes along with that is if you just take p to the n, just the nth power of the matrix, this will converge to the matrix that just has pi as all of its rows. Okay, so I've given you kind of a really brief overview of things that happen in Markov chains. So how would you actually go about solving this problem? Well, the reason this problem is still difficult with all this general theory telling us what to do is that there's a lot of states, because we've got 5 letters. We got 6 letters, and we have 5 spots to put them in. So we have 6 to the 5th, which I punched into a calculator a second ago, is 7,776 different. Yeah. That's how many possible states we have. So if you wanted to actually do this, what you would do is you would start with your 776 by 776 matrix with all the transition probabilities, and then you can either compute the steady state distribution by doing the eigenvalue 1, or you could compute it by raising this matrix to a larger and larger powers and taking the limit. But I'm going to say probably this, because I sure don't know how to do the large power thing. Once you do that, you take the component of this vector that corresponds to the word rotor, and this will be 1 over the mean recurrence time to the word rotor. This shouldn't actually be very hard to do because, well, this is a freakishly huge matrix, but it's very sparse, right? Because in our scenario, each state only leads to 6 states, which means in our matrix, in any given row or any given column, is it row or column? Or both? I'm not sure. I would have to sit down and think about it. But at least in one or the other. I guess it would be any given row. There's 7,770 zeros. So in principle, this shouldn't be that hard to do. But again, I'm not a sparse matrix guy, so I don't actually know how. But anyway, in principle, to compute that probability, you just write down this huge matrix, which has lots and lots of zeros. You compute its row eigenspace for lambda equals 1. You look at the component for rotor, which this will be a vector with 7,776 entries, a row vector. You take the one that corresponds to the word rotor, take 1 over it. That's how long on average it takes you to get to the word rotor. So in principle, that's how you solve that type of problem. All right, well, hopefully this was helpful. And yeah, hopefully it was fun.